Well, good morning. I think I was the first one that ever published any ozone generation data of krypton chloride lamps, and so it's fair, maybe fair that I'm the last one to uh, participate here. First, I want to say thank you very much for all your research and contributions. It's very important, and yeah, we have to work this out. It needs consideration. There's no doubt that krypton chloride lamps will create photo reactions. It's well known. It's already used in water treatment and other operations. So, but I want to take a more practical look, and for the 10 people in the room that still haven't got the whole grasp, what is it with the ozone and krypton chloride, maybe giving another approach. So I recorded the data of published ppb per hour rates with the same lamp, and nice graph. I found out the only correlation factor here is how many days are left to the Far-UVC conference. That's a joke, yeah. But it's for someone not familiar, it can look very confusing. What is it? One? Is it 300? So I want to talk about this. Main problem is we come from ozone generation devices, and all these devices that are out there in the world that create ozone with photons are measured in micrograms or ppb per hour. And of course, when we started working with krypton chloride lamps, that was the technology that we used to measure it, and we came up with some values. They were low, and but then nobody ever complained. Nobody smelled ozone. People had devices certified UL 867, no problem, flying colors. Now, thanks to the colleagues that are much more familiar with photonic chemistry, yeah, it occurred to us, yeah, something is wrong. And the main difference is the absorption lengths of the wavelengths. And I listed them here, typical xenon excimer lamp, 172 nanometer. It's only 6.2 millimeter for 90% absorption. Typical mercury lamps, 185 nanometer. It's already 27 centimeters. And for a krypton chloride lamp, 750 meters. So you could say, well, we ignored that, but we learned the hard way. We must not ignore that. But it has severe consequences how you measure or calculate the ozone generation rate, because suddenly your room becomes the device, and the ozone generation rate depends on the room size. For those that are familiar with the pathogen reductions, I thought I lead you a little bit through the math, because there's similarities, and that makes it maybe easier for you to understand. So it all starts with a simple differential equation. The solution is essentially always the same. And there is this steady state concentration, and that is basically just the source divided by all the reductions summed together. Where it is different, when we talk about ozone generation, we have a source generation or ozone generation that depends on the fluence rate. And with pathogens, we don't have anything in the source, but when it comes to ozone reduction, as we heard, photonic destruction of ozone by 222 is negligible. So we have various factors that reduce the ozone in a room, including the ACH. And when we talk about pathogen reduction, we have our famous EACH plus ACH. Just a note, whenever the reduction rates appear in the exponent, that's where the questions come up. Can we use average fluence rate, or do we have to really do fluid dynamics and get into the little nitty-gritty? Yeah, and one important thing I should have highlighted that, yeah, fluence rate is not irradiance. It's something different. When we talk about fluence rate, that's in a volume. Irradiance is on a plane. So that of course leaves the questions, how do we determine fluence rates? That's the big question in air disinfection as well. The absorption cross-section and decay values. I already said, fluence rate, we have to talk. I think all of us, we have to better understand and talk with the same terms, irradiance versus fluence rate, ACGI, HDLVs, and all of that. Not today, but I want to make you aware there is still a lot of confusion, the wrong terms and the wrong measurements are applied and so on. Problem is there is no fluence rate meters in the market at the moment. And so the only reasonable approach today is that we can use pretty good computer programs and simulate rooms and setups, and we can calculate the fluence rate in a room, I think, fairly accurate. And I'm very excited about seeing the approaches with actinometric methods that have been taken by Colorado and the others. I hope to see more of that, and especially that over time we also calibrate it against actual irradiance or fluence rate measurements. For you out there that don't have the program, a sanity check, I would call it, how to calculate fluence rate in a room. Take the power of the lamp, multiply it with the longest path length that you have in a room and divide it by the wall. That gives you a first good approach to the fluence rate. Anyone that installs devices like that should at least do this calculation. It gives you the upper end of the fluence rate. If you do the more detailed calculations, it will be probably 10 to 40% less, and with multiple lamps, and depending how close you are to the wall, it can get complicated, and especially if you have high reflective walls, all bets are off with this formula, for instance, with stainless steel walls or Teflon walls and so on. That gets really, really tricky. The most important thing is when you install 222 devices, all GUV devices, the first thing you want to do in the planning process is calculate peak irradiance, not fluence rates. ACGIH has not the word fluence rate in. It's irradiance, and one is vertical, one is horizontal. But that is the limiting factor. The irradiance at a certain height is the limiting factor, and if you have too much, you have to dim the lamp down or use time-weighted average to get into the right range. Now, ozone reduction. What we heard today were, I call it lab studies, very well done lab studies, but let's say usually we don't operate in a Teflon or stainless steel chamber. Fortunately, all these ozone things are not new. There's research going on and publications for over 50 years, so there's data out there. So the one important thing you may want to remember, the ratio between outside ozone and inside ozone is typically between 15 and 25%. I was outside today, measured somewhere around 25 ppb, very nice day in New York today. Inside we have somewhere around 8 to 10 ppb today. The most important thing, and it has been mentioned before, as soon as you have a filled room with stuff, furniture, carpets, walls, and so on, and it's quite surprising. And they measure that in the same unit of measure as we measure ACH, so it's per hour. So you just use it in the same formulas together with the ACH. You basically add it to the ACH. Typical values are 2.8 plus minus 1.1. I would say if you start with a value of 2 per hour, you get into a pretty decent range. Another one is occupants. So us being in a room, we absorb ozone. And they came up with a number of 0.09 per person. So if you have 10 people in there, you get another 0.9 ACH on top. And then it gets a little weird. Nitric oxide is extremely absorbent to 222 and for ozone, high ozone reaction rates. But now in our typical environments, NO is probably not a big thing. And I will not get into VOCs. We had already our talk about that. So the big problem that we as practitioners, not specialists of ozone, have, so how can we predict the ozone generation rates or the ozone levels in the application? And it has been said before, formula is pretty clear. The main thing for me is the values that we have at the moment in ppb per hour or in microgram per hour. These values are room size dependent, and they are fluence rate dependent. Yeah, and the fluence rate depends on the room size and so on. We as end users need numbers that we can scale with the room. So what, yeah, you look at these values, that's what has been measured. Yeah? And we have fluence rates. Not sure how accurate they are. I have some doubts, but then I divide the ppb per hour by the fluence rate, and not that close. I think that needs further review and refinement. But what I want from you, scientists, is a number for, let's say, our lamp that gives me ppb per hour per 1 microwatt per square centimeter fluence rate. Then we can plug that number into our software where we calculate fluence rates in rooms for air disinfection anyway, and we get a good starting point for the ozone generation. I really ask you and want to put that on your task list to come up with one number. In principle, I don't care if it is 10 or 7, but sit down and analyze why the numbers vary. And I think we have specialists here that can also help you with maybe refining the fluence rates. But that would help us very much. So, and then of course, once you have all these constants, you can do all kind of calculation and simulations. With some realistic settings, you get between, let's say, 2 and 5 ppb increase in a real world setting, depending, of course, on the ACH, and you can calculate steady state values depending on ACH and depending on the fluence rates. And then, yeah, there's few advantages of getting old, except that you may end up with an empty kids' room at home that you can turn into a little ozone home lab. That's what I did. So I borrowed a real ozone measurement device from the company, and had a couple lamps, B1 modules, and then I turned the lamps on, and what happens when I do this and that, and so on, and oops. So yeah, you turn the lamp on, and you see raises about 7 ppb in the room. Pretty close to prediction, of course, as long as I can adjust all the constants that I put into the models, and it's not unexpected. I can tell you one thing. ozone measurements fall fully under Murphy's law. Whenever you have a successful experiment, don't repeat it. Yeah. Because yeah, every day almost these values look somewhat different and so on. And I only give you some indications. And at the same time, I had a cheap Chinese indoor quality meter, and I recorded these data. And so I have them basically, and I can at least see you if there is an influence. I'm almost finished. So what you see is the biggest influence is when I open the door, and that is in sunny California, the window in sunny California, yeah, the values jump up by 15, 20 ppb. And then they slowly come down. That's all what it is. But the important part here is, so when I turn on the lamp, the VOC in the room with this device, of course, didn't change any meaningful. I had closed all the ducts and so on, and still I see this thing when my AC unit came on. It just pressed some fresh air under the door. And of course, let's never forget, yeah, the ozone may go up, but opening the window really cleans the air. So important. And then I took a B1.5 module. No, I should go back. These measurements that we heard before, they were basically done almost similar like this in a bigger room and so on. So you take our B1 module, you shoot it across the room. Fluence rate modeled is about 1.7. Now, that's not the way how you use the lamp. The way you use the lamp is probably you put it in a ceiling, you shine downward, you measure ACH irradiance values at, yeah, optimistically 1.8 meters. And then I would have to dim the lamp to 40% just to get to 480 microjoule per square centimeter. 40% of that output. Yeah. And I'm still on the very, very high end of the ACGIH. And with that, I end up with 0.6 microwatt per square centimeter in that room. Keep that in mind. The measurements and the assumptions of some of the previous ones, they were more based on something like this, but in real world, you have to dim the lamp down. And B1.5 module, because it is much lower output, I don't have to dim down. And then unfiltered lamp, I can confirm unfiltered lamps really bump up. Yeah, is that 30 ppb. So I recommend not to use unfiltered lamps, obviously. And then having some fun, putting some flagrants in the room and so on. And I did not really see any measurable influence on the decay rate, depending on the lamp also, because your measurements are much more accurate. I will not argue ever. My last slide, something to think about. In hospitals, we are using disinfectants. That is the most standard method. When you use disinfectants in hospitals, you will create a lot of aerosols as well. All that stuff evaporates. And I mean, you get into levels of VOCs that you can never ever achieve as a lamp. I think this part should at least be part of the considerations when we talk about death and risk and so on. Yeah, what else will we do if we implement strong restrictions on VOCs or ozone or whatever? Will we ban disinfectants in hospitals, or what do we do instead? Anyway, I can only repeat, it's very important to take these measurements to analyze the situation, to contribute. Really what I wanna get is, again, one number for the ozone generation per affluence rate. I would very much encourage you to continue with actinometric measurements and coordinate between each other and verify that the results are the same. And the only other thing I would ask is maybe think about the titles of your publications and the conclusions, because there is a chance that with your reputation and your comments, all the good things that we are trying to do with 222 will be derailed in a heartbeat, because many people will not understand the little nuances and so on. So I ask you to think carefully how you word your result. I will never even argue about your scientific results. It's more a question, how do we present them to the public? How do we come to conclusions that benefit humanity and everyone? And that's it. Thank you.